Yeah, so I guess this is going to be interesting. My name's Naif, and I'm the first of many presenters today. Today we're going to have a presentation by committee here, and we're all supervised by Professor Paul Chow at the University of Toronto, and we're going to go over from a high level on Galapagos, which is our multi-FPGA platform, and the stack, a multi-FPGA stack of sorts. So each of us could probably do a full presentation, but here is a really high level overview of everything that we have. And if you have any questions or want more details or even want to have any one of us talk more in detail about anything, you can let us know after. All right, so I'm gonna begin right now. Okay, so let's see here. Okay, so to start with, data centers especially are becoming more and more heterogeneous, right? So we've seen Microsoft put in FPGAs in the data center. There are also GPUs in the data center. People are looking at putting things like TPUs and other accelerators. So it's getting more complicated, as well as we have more contingent requirements on our applications. So we would ideally like to make better use of this heterogeneous data center for our application. So on the left-hand side, we have this distributed flow diagram of what could potentially be a heterogeneous application, but the users doesn't know what kind of devices they want to target. So they have something agnostic to the actual accelerators. On the right-hand side, based off of requirements and the application itself, that multi-node application gets partitioned into different kinds of devices. So some could be CPUs, some could be GPUs, some could be FPGAs, or whatever you have in your data center. So this is, and the holy grail would be, without any user intervention, we go from the left-hand side to right-hand side. So we're not there yet, but hopefully that's in our roadmap. So in order to get that, we want to take advantage of the unique resources, and we might need to make abstractions for these devices, or at the very least a backdoor for these devices to communicate. And scaling this up is difficult. Many of us work with FPGAs. One FPGA is painful. Imagine a data center of them, and imagine a data center of many different kinds of nodes. So this is our philosophy here. We have a heterogeneous stack, where on the right-hand side is something you might be already familiar with on the software world. Well, here we have what we have on the left-hand side, which is the hardware equivalent. And along with that, we have a way for the hardware and software to communicate. So to start with, at the very bottom is the physical hardware. So this refers to the physical devices and how they're connected. So this could be FPGA, CPUs, or whatever devices that you have. In this picture, I have a dinky setup of my own data center in quotes, and here's like a Nexus board with my laptop and a 1 gigabit switch. But more interestingly, on the left-hand side in this diagram here, I have another data center with a bunch of MPSoC boards here. The approximate cost of data centers on the left-hand side and the right-hand side is 50x difference. But the takeaway is that with the same abstraction layers, it can work on both data centers. So a user with the right abstractions, a user doesn't have to code any differently for if they have the right-hand side data center or the left-hand side data center or anything in between. So how do we get there, right? So we have a hypervisor which abstracts away an individual node. So this also in the Microsoft speak is called a shell, and it abstracts away all the I/O devices for any one of these individual nodes. So it's for a CPU or for an FPGA or so on and so forth. And we would have one different kind of shell for each board type. And Daniel in the future will go into more detail about this. But the main takeaway is once we apply the shell, each of these nodes looks the same. So they're a stream in and a stream out device. And since they all kind of speak and connect the same way, we can connect these nodes together. So I can connect an FPGA's stream out to the stream in of a sensor. I can connect the sensor stream out to the stream in of a CPU, for example, right? So we have the framework to connect all these nodes together, but you can still imagine that doing this at scale can be quite painful. So for this, we have the middleware layer. So this refers to how we orchestrate clusters of devices, and we want to automate the connection of all these devices as well. So from a high level, we have what's inside the red box here, which is a flow diagram that I introduced at the very beginning, closer to the Holy Grail. Again, this flow diagram is agnostic to actually how these IP cores are going to be partitioned in our network. Along with that, we give some sort of helper files to say, oh, these are the amount of nodes that we have, and this is the resources available for each FPGA in our data center. Based off of that, our tool can actually partition this and say, okay, I can greedily put this many IP cores in this node, I can put this many IP cores in this node, and depending on what we specify as our off-chip communication protocol, it would be connected in that way. So for example, these nodes may be connected with TCP, these nodes may be connected with UDP, so on and so forth. Our logic here automatically does the bridging to make that happen. So these kernels all communicate in axis stream, but underneath the hood, it gets converted to network packets if it has to go off chip. And as a user, you don't have to worry about any of that. So it goes through our tool flow and we get the output that we see on the right-hand side. And on the right-hand side, you'll see these IP cores, these axis stream IP cores are split across multiple nodes, and the communication amongst these IP cores, whether or not it's on the same device or on a different device, is abstracted away from the user. So it generates these IP cores. Thought I got rid of these slides, sorry. And lastly here, we have the communication layer. So this communication layer is used to connect a CPU node to the hardware node here. And the idea is that in a CPU world, all the IP cores that I've made there is an equivalent in hardware. So for a CPU kernel, it can communicate to hardware kernel without explicitly making a different kind of node. So it's seamless. So I can seamlessly take things from CPU and move it to hardware and vice versa. And at that note, I'm going to hand it over to Daniel, who will go into the shell builder.
Thank you, Nath. So with the shell builder, this is like in progress work that we're currently working on. And the idea is to have a project that can build a shell. So let's just get started with what is a shell. So a lot of people probably already know from the Microsoft nomenclature, but it's basically that boilerplate hardware that we kind of include in every design. So it provides access to the external interfaces or resources, usually abstracts access in some way to those resources, whether that's just a simple AXI interface or something more complex like TCP or UDP. And then there's also arbitration for those resources. So typically that's in like a multi-tenant shell where you have multiple applications on a single FPGA, but it could also be in like a host and application arbitration. Something to note is that in a multi-tenant environment, we also have like security hardware and isolation hardware that we implement, and that's work that we've done in our group as well. So we do have that kind of hardware in our shell. So we have this distinction in our group of a hard shell versus a soft shell. So the hard shell is basically in a PR flow, the static region. So we include only those things that absolutely are required in the static region in this hard shell. So that's going to be like the interface access, arbitration, security, isolation, any of the PR control stuff. And then any features of the shell that aren't required here, we push into the actual partial bit stream. So portions of the shell can be synthesized together with your application or your kernel. And this is where we include any OS-like abstractions, so higher level abstractions. And the logic here is space on the FPGA is limited, so let's just put the higher level functionalities and instantiate them only in the partial region when we actually need them. So here's kind of a depiction of what that would look like. So you can see in the static region, you kind of have the controllers and all this isolating hardware. And then inside the PR region, we have a layer of shell, which has some examples of what these abstractions might look like. Maybe MPI, TCP, file access, depending on what you need. When we talk about the shell builder, though, we're kind of just talking about the hard shell. So how do we build these, the static region for all these different situations? So with their shells, we're always redesigning them, for targeting different boards, different interfaces. In different situations, you might want different number of PR regions or different interfaces per region. So how can we make the shell building easier? And that's where we have the shell builder. So again, this work is still in progress, and obviously the name is in progress. It's pretty simple right now. We can split this up into layers. So we call something the file layer, the physical layer, those components that kind of change on a board-to-board basis. These are the physical interfaces, the clocking, the reset, host connectivity, stuff like that. And then the common layers are those components that don't really change between boards. So interconnects, isolation cores, things that we design, and register slices. So here's a depiction on my previous figure of what that separation looks like. So the file layers, the controllers, and the common layers is kind of everything else. So how do we do a shell builder? So for the common layers, it's tedious, but it's pretty easy. You just have a massively parameterized HDL. So we use system Verilog. So you parameterize a number of regions, interfaces, the parameters of those interfaces, basically every detail. And then you use standard system Verilog interfaces to kind of make things a little bit easier. So all the components can be optionally instantiated, interconnected based on these parameters, and that kind of makes you able to build a shell based on your different configurations. For future work, we'd want to implement a higher level flow that kind of generates these parameters from some kind of descriptor file, and that's just because the parameters as they stand are pretty complicated to understand for a typical user. Going to the next layer, the physical layer. Right now, we still manually create our physical layer on a per board basis. There's a little bit of parameterization. So for example, if you have a QSFP port, you can optionally include that with a parameter as 100 gig MAC or 4 10 gigs or 425s, which eases some of the shell building, but obviously not fully parameterized. So can we automate this any further? So this is our hope for a full shell builder. This is the physical layer, the phi shell side. So what you see is if we have a board descriptor and some kind of configuration file, can we create some script here that generates wrappers for every possible configuration of each of the interfaces described in the board description file. And when I say every possible configuration, I mean every configuration that has a different top level interface, because that's the only place where we need a unique Verilog that can be instantiated within our system Verilog phi shell that's parameterized. Any other configurations that can be different within an interface can be specified in this configuration file. So we won't need a separate wrapper for it. But here's an example for a QSFP port with 5 different configurations. We repeat this for each port, and then you could parameterizedly include them in your phi shell. If we couple that with what I described for the common shell, so I described the system where we have a high level system for creating the parameters, and then these parameters can be used to parameterize both the phi shell and the common shell to create our full shell. Now this works fine if you don't have PR, like this is the final flow if you don't have PR. If you do have PR, you still need to consider floor planning, which is a little bit more complicated. And this is kind of the idea we have for now that we're going to implement. So once you have the shell, we have a step for manual user hierarchical floor planning. So we floor plan hierarchically, but then we also have a database for storing the place and route results for those different hierarchies. So that way, if you want to change something at a higher level of abstraction, you don't have to replace and route the lower levels. But is there some way to automate this more? That's something we're currently thinking about. So that's our shell builder. I'm going to pass it over to Clark to cover the interconnects.
Thanks, Daniel. Hi, my name is Clark Shen. I'm going to talk about the data center interconnect. Nate, could you give me the control?
Yeah. Is this bug again? There you go.
Okay. So speaking of data center interconnect, emerging applications such as RDMA and large ML applications nowadays need the network interconnect to be lossless, high bandwidth. When we talk about high bandwidth, we usually means it at least 100 gigabit per second. And we also need a low latency. So it's almost a common sense now, the conventional TCP IP stack is far away from grid in this context. We observe 2 major reasons that make TCP IP inefficient in data center. The first is that the end-to-end acknowledgement and retransmission mechanism harms the bandwidth and latency a lot. The second reason is that nowadays data center administrators want to do things such as congestion control and dynamic bandwidth allocations to satisfy the constantly changing user needs. The best place to perform these operations is within the network switches, because the switches have the power to monitor and dispatch all the traffic. However, the network switch we use nowadays in the data center works fundamentally as the same way as they worked 20 years ago. So by looking deep into these 2 reasons, we found a way to our approach. So let's first have a look at the retransmission. So this figure at the left is a conceptual illustration of retransmission. So A send a frame to B, B would wait until the last bit of the frame to arrive, to examine if it's a good frame. In the case that is a corrupted frame, B would send back a retransmission request to A. Or in some other case, A would itself would have a timeout mechanism. So either way, when the retransmission triggers, A starts to resend the old frame to B. So the retransmission buffer needs to be big enough to cover the data sent between the time A sent the first bit of frame until A received the retransmission request. The longer the time is, the larger buffer size will be required at the end device. So the delay, we call it retransmission delay, is positively correlated to the link delay. And in the case we do end-to-end retransmission, the logic link would include multiple physical nodes. The link delay contributes the majority part of the retransmission delay, resulting larger buffer size usage. At a certain point, the end device cannot use an on-chip memory anymore. They have to use an off-chip memory, which further increases the latency. And second, let's look at the congestion control. So in the case we can't do any modification on the switches, we have to use end-to-end congestion control. It works as this. So A send packet to B. When the packet go across the congestion node, let's say software switch 2, the switch 2 will turn up the congestion notification bit in the packet. When B receives the packet, it sends back a congestion notification to A. The end-to-end congestion control works at very fine-grained level because the notification can be sent based on per flow. However, it is very slow because the packet has to go through all over the round trip. It requires larger buffer for the end device. However, if we do hop by hop, it can be pretty agile, requires a lot less buffer for the end device. So here goes our approach. So we built link layer and we rebuilt the link layer and network layer. For the link layer, we made it lossless and we have the hop by hop retransmission. For the network layer, we implement a flexible FPGA-based switches, which has the switch-initiated hop-by-hop congestion control to guarantee it is agile. And we have the end-device-initiated end-to-end congestion control to guarantee the fairness between flows. So our ultimate goal is to build a data center-wide network interconnect that achieves high bandwidth that at least 100 gigabit per second and within less than 300 nanosecond per hop latency. And it can be multi-hop and the device can be plugged in, plug out at a runtime. And the administrator can do dynamic bandwidth allocation by themselves. And it has to be lightweight, consumes less than 2% of the usage per FPGA. So the green part is what we already achieved in a small scale experiment. Eventually, we want to meet all the metrics and implement it at the data center wide. So that's the end of my part. I'll pass it over to my colleague, Marco. He'll talk about the high level debug for FPGAs.
Thanks, Clark. So my name is Marco, and today I'll be talking about our debugging tools for Galapagos. First, I want to talk about debugging in general. The execution of a program yields a value at each point in time for inputs, state variables, and outputs of the design. A bug is something that went wrong in one state and possibly polluted an entire cone of influence from that point forward. This state-time search space can be huge, so how do we ever manage to debug it? The answer is with heuristics. We selectively disregard details based on our knowledge of our design and the underlying technology. For example, maybe by looking only at arguments and return values of a function, we can eliminate all its internal variables from our search space. And maybe with some other simple tests, we can rule out that the bug first occurs after a certain time or before a certain time. Once we've cut out several large areas from our search space, we can start looking at individual variables and single stepping. I use the term low-level debugging to mean careful single stepping and high-level debugging to mean coarse heuristics for quickly reducing the search space. Now, the search space isn't fundamentally different on FPGAs. The state is now registers instead of variables or structures, and the time is now in clock cycles rather than lines of code or processor instructions. In some ways, the search space is bigger, but the real killer is visibility. ILAs or signal tap, provided that we remember to add them in, can help us by showing us a small window into this search space. Usually, we're limited to seeing only a few wires for a short time. There are techniques which can make this window bigger, but if we didn't catch the bug, our only recourse is to move the window, which usually requires a recompile. And this is like scrubbing a whole building with a toothbrush. Of course, simulation fixes the search problem. I can see the entire search space. And simulation is a necessary but not sufficient debugging tool. Writing test benches is difficult, time-consuming, and error-prone. And it can be difficult or impossible to recreate the exact conditions of a bug in simulation. So at this point, I'd like to recap on the problems we're trying to solve. Searching the FPGA state time space with ILAs is slow and painstaking. For that reason, we'd like to have any kind of higher level debugging tool. And while simulation is the best tool we currently have, it shows its limitations by being about as painstaking as using ILAs. More than that, I've often encountered bugs that I couldn't recreate in simulation. Sometimes it's because the generated FPGA hardware differs from the standard Verilog semantics in the simulation. And sometimes it's because my own limited understanding of the bug didn't tell me what I was doing wrong in my simulation that was happening in the FPGA environment. And I've listed 2 bonus problems, which I'll talk about again when I'm at the end of this presentation. So our debugging approach specifically targets data flow computations, which map very well in Galapagos. In this scenario, you have a number of compute kernels all connected by one-way streams. We prophylactically add special instrumentation. These elements, which we call governors, can pause, log, drop, or inject flits on any stream. In particular, we stress the importance of supporting injection, as very few debugging tools allow you to interact directly with modules in your design. More importantly, however, the governors support any simultaneous subset of these 4 operations. For example, by combining pausing and logging, we can do single stepping. Or, for example, by using all 4 operations in different parts of a design, we can bypass a core. This effectively lets us move part of our design into a simulator without disturbing the rest of it. And you won't even need to write a test bench. So how did we do in addressing the problems we set out to fix? Since each debug governor is very lightweight, it's easy to have several dozen or even hundreds in your design. This significantly improves visibility while taking advantage of higher level debugging. Our technique of replacing cores with a simulation can make it possible to run a faithful simulation, but only in the case that the much slower model doesn't affect the rest of the design. Lastly, we point out that our governors don't store log buffers on chip. Instead, if the logging interface is bottlenecked, the governors will pause the underlying streams. This makes sure all the logs get through, but it doesn't solve the Heisenbug problem, or in other words, bugs that either start or stop happening because the instrumentation changes the design's behavior. In our future work, we want to take our governors and extend them to use more protocols, for example, AXI memory map protocols. Also, because the governors can pause the underlying stream, we would like a way to maybe reduce this or eliminate it. And that way we can help with Heisenbugs more. And finally, we'd like to combine this with some of the performance monitoring techniques that Arjun is going to talk about in a second to give a more complete instrumentation in Galapagos.
Thank you, Marco. And hello all. This is Arjun, and I'll be talking about Pharaoh's multi-FPGA performance monitor. By performance monitor, we mean instrumentation that monitor different metrics within the network. These metrics can be latency, throughput, bandwidth, or other network-specific metrics such as total number of packets or flits, or the average packet size. There are multiple benefits in monitoring performance. One of the biggest use cases is optimization and debug of the system. Let's say you have a simple model of a network like the one you see on the right, where traffic on the links is visualized by colors, red links being more busy and green links being where there's less traffic. A performance monitor can help us answer this question as where are the slow regions of the network. And we can use that answer to debug and optimize our system. Now, instead of the network links, if we look at how busy each node of the system is, we arrive to a complicated problem in clusters, and that is the problem of placement, which is finding nodes on the cluster that best suit running a new task. When a new task or application is to be run on the cluster, we want to find the idle nodes and avoid the nodes that are already busy. And performance monitoring can help us in finding the regions that are best suitable for running a new task. Another useful benefit of performance monitor is behavior modeling of certain applications, more specifically how a certain application affects the traffic, how much bandwidth it uses, and what are its throughput and latency. Now let's look at some of the techniques used in our performance monitor, Pharos, starting with latency measurement. Let's say we have a simple network with 6 nodes, and we want to measure latency for the packets that are going from node 3 to node 5. We can do this by simply timestamping each packet and sending them from node 3 to 5. But there's a big problem, and that is that these 2 nodes are running on different clocks. And any tiny difference between the clock speeds will cause their times to drift apart, and that can affect our latency measurements. An easy solution to this is to send packets from 3 to 5 and then back from 5 to 3 and measure a round trip time. Yet an even better solution is to introduce a notion of a global time to our system. And this can be done, as it is done in Pharos, using PTP protocol. PTP, or Precision Time Protocol, is an IEEE standard. In the scheme, we choose one clock as the master clock, which all other clocks will synchronize to. As you can see on the right, the node 2 in this case holds the master clock, and all other nodes have the slave clock. And this can help us measure latency by one-way trips of packets. PTP has 2 main steps. The first step is when master sends a synchronization message to the slave with its time, then slave updates its time to the master's time, and through a back and forth communication, slave measures the network delay and adds the offset as a correction. IEEE recommends this procedure to be repeated every 2 seconds. In Pharos, there are multiple alterations made to the PTP protocol, taking advantage of the programmability of the FPGAs. As you can see on the right, the initial synchronization is eliminated, making the protocol simpler. In this case, the initial synchronization and the network offset correction are all done in one step. Also, each slave can have a different synchronization period based on whether its time is drifting apart from the master's time less or more rapidly. Pharos also has a bandwidth monitor. It collects traffic information by snooping on axis streamlines. Packet Snooper collects information such as number of flits and packets that pass through axis streamlines. The duration of the measurement is also collected, and therefore we have the means to calculate throughput. Also, average packet size is measured by the Packet Snooper. A few things that are going to be done in the future: integration of Pharos into Galapagos, adding event logging or tracing systems, extending the system to work with other protocols, and developing a user interface. I'm going to pass it to Camilo to talk about shift storage system. Thank you.
Thank you. My name is Juan Camilo. Today I'm presenting the chip storage system. The overarching goal with the chip system is to have a storage node that is accessible throughout our data center. This is not currently possible because the lack of scalability in current protocols and file systems and inode data structure navigation is highly complex and serialized. And this is especially an issue because the standalone model for FPGAs is becoming more common in our industry. Now, this is an image of the current storage system, and on the left is a standard off-the-shelf SSD connected via PCIe to the CPU system that has At the lowest level, a root complex performing the physical interface. On top is an NVMe driver that handles creating the PCI messages. This is utilized by the OS file operations driver that handles the file system navigation and inode navigation and exposes an API that then the user application can use. This storage driver is incredibly complex, and it is what we aim to simplify so that it can be done on FPGAs. So one approach found in the literature is to change the SSD itself to one that exposes an API that solves our issue. But we want to use off-the-shelf SSDs, and file system and inode navigation still needs to be done to find out where our data is located. And the small processor on board the SSD is just not powerful enough to be given too much more jobs. We look then to the RDMA protocol. Now, this is not a storage protocol, it is a protocol for high-speed memory-to-memory transfers. In the RDMA world, a CPU process can expose a portion of its virtual memory space to any network-connected device that has the correct password. Remote users access a specific offset within the RDMA queue in a way similar to how storage users would access a specific offset in an open file object in storage. RDMA is very fast. For CPUs, ASICs in many data center grade network cards can already perform RDMA processor in hardware, bypassing the CPU altogether. And this is a heterogeneous standard with FPGA and GPU support available. And so we propose the SHIP storage system. Again, we're using the same commodity, PCIe connected SSD. But now we build a shell that pre-processes and simplifies the storage interface and internally performs the complex portions of the storage navigation. This shell exposes an RDMA API, which makes the storage device look as if it was an RDMA accessible memory node in the network. It is only the human operator that knows that this so-called memory is actually a non-volatile storage device. But in the perspective of the drivers and utilities using it, it's a memory. So there's no need for a new driver to handle it. And this allows for a much simpler driver to be used, consisting of a simple network driver, an RDMA interface, and a UDP bridge. And we use a UDP-based protocol to manage file operations such as open, close, and seek. All three drivers are already available for CPUs, GPUs, and FPGAs, and the system is network connected, allowing it to scale better in our data centers than PCIe. Thus, we have built a storage system with simple driver requirements, but that does not sacrifice in features. SHIP SSDs can be formatted with any Linux-compatible file system with no limitations to what users expect. It is network accessible for better scalability. In CPUs, since much of the compute is offloaded and ASICs can be used, the computational requirements drop. This is the resource utilization of the SHIP server itself. Less than 20% of on-chip logic and 40% of on-chip memory is used. There's plenty of room left over for future improvements of this system. But of more interest perhaps is the utilization of the driver IP that is added to the user's shell, which we aim to make as small as possible. Logic utilization is under 2% for this IP with the XCSATU19EG FPGA. We built an application on an FPGA that used SHIP to store video data instead of offloading the storage task to the attached CPU. This was not previously possible, and the FPGA was able to sustain a continuous storage bitrate of 294 megabytes per second. We compare this to the throughput of the same application on the same FPGA, but with an AXI-connected ARM in the conventional approach of forwarding the storage to the CPU. The maximum throughput decreased to 1.85 megabytes per second. We also measured the write latency of SHIP on the CPU and found it to be much lower than NFS or local storage, primarily because the compute-expensive file system navigation was no longer necessary. File system navigation dominates latency at small sizes, hence the large difference. In conclusion, we have been able to build an FPGA-compatible storage system that accomplishes this view of the data center, that allows all processors in the data center to have a fully featured access to the storage server. It also leverages existing data center ASICs to improve performance. We have achieved a considerable throughput of 294 megabytes per second, and we operate at a very low latency. My colleague Varun will now showcase his memory infrastructure.
Thanks, Camilo. There we go. Okay. So hi, everyone. My name's Varun, and I will be talking about PGAS for Galapagos. So PGAS is a memory model, and it stands for Partitioned Global Address Space. Before I explain what that means, let's talk about memory models in general first. So in parallel computation, a memory model represents the abstract view of memory from the perspective of the software developer. The model affects how nodes communicate data and therefore how code is written and structured. To give PGAS some context, I'm going to talk about two other models first. The first is perhaps the most familiar, which is the shared memory model. In this model, the parallel kernels have access to the same memory, so no explicit communication is needed to share data. In the opposite model, is the distributed memory model, where each kernel has its own private memory space. In most popular implementations, communication between nodes occurs through message passing, which is also known as two-sided communication, which I'll get into a bit more later. Now, PGAS is a hybrid of these two models. In this model, memory is still physically separate, as in the distributed model, but it can be thought of as logically contiguous to emulate shared memory in some respects. So why use PGAS? While shared memory is familiar and convenient, the major issue is that it doesn't scale across many separate nodes, which is a problem in an inherently scalable infrastructure such as Galapagos and in an environment like the data center. In contrast, PGAS scales well like distributed memory. As I mentioned before, distributed memory traditionally uses two-sided communication using send-receive semantics. For example, if the blue node wants to send some data to the red node, it would need to call some sort of send function, while the red node would call some form of receive function. This establishes the communication or the data exchange between the two nodes, and that is needed it needs to be synchronized between the two nodes. The use of this communication pattern requires a programmer to ensure this synchronicity and ensure that the order is correct, like in the case if multiple kernels need to exchange data with each other. PGAS, one of the central tenets is the idea of one-sided communication, where the node in question can independently interact with another node's memory without involving a kernel there. In this way, one-sided communication is easier to write than two-sided, and it's more akin to the familiar communication patterns in shared memory, where data can be freely exchanged. Of course, to enable this functionality, we need some additional support on each node to handle these requests. So in broad view, the PGAS on Galapagos, as you might suspect, provides support for running PGAS applications on Galapagos. It is an application programming model at the highest layer of Galapagos, and it leverages all the infrastructure below that my colleagues have been talking about. In software, this corresponds to taking advantage of libgalapagos, the C++-based template library for communication among software and hardware Galapagos kernels. In hardware, it means that the IPs fit into the application region of the Galapagos shell and are built as part of the default Python Tcl script flow. There are two main deliverables here to enable PGAS. The first is the C++ source and headers that define the API for communication. The API is similar for both software and hardware implementations, so kernels can be moved between them. They work in the hardware case through Vivado HLS, and you can just import the headers and include the headers and use them. Second, there is the PGAS engine on the FPGA that facilitates the one-sided communication by sending out local messages from kernels and responding to remote requests. And that is PGAS on Galapagos in a nutshell. So I'm gonna pass it off to my colleague Mohammed, who's gonna talk about deployment and orchestration. Thank you.
Thanks, Varun. Naif, thank you. Okay, hi. My name is Mohammed Awais. Today I'm going to talk about deployment and orchestration of FPGA-based applications in data centers. So let me start with a little bit of background. First, going to talk about Docker containers. So Docker containers, as some of you may already know, they're a way of running applications in isolation from each other and in isolation from the underlying hardware. This allows for portability, security, and perhaps scaling. As you can see, each container will only have one application plus the libraries and resources that this application needs to function. The containers run on top of the Docker runtime system. And well, theoretically, you can think of those as lightweight virtual machines, as they provide the virtualization, but they do not run against the operating system. The second bit of background I'm going to talk about is Kubernetes. And to understand what Kubernetes is, I'm going to throw a little analogy here between the processor and the data center. So the same way processors have cores, data centers will also have nodes or servers. And in the same manner that cores will be able to run threads, in the same manner that cores will be able to run software threads, then the nodes in the data center are also running containers. And in the same manner that we have an operating system to manage and schedule all those threads in the processor, then we also have Kubernetes in the data center to manage and schedule all those containers together. Of course, they are marginally different in the way they do scheduling. They are not the same, but that's the general idea. So let's assume we have this server. We have a CPU and an FPGA connected together through an AXI or a PCI Express. Assume we run a Docker container on this. So the Docker container will eat up a chunk of the CPU resources, but it's completely agnostic to the fact that there is an FPGA. It doesn't know it, doesn't understand it, it doesn't deal with it. Ideally, we would like to modify the Docker runtime system itself to natively support FPGAs and utilize them. But for now, we have a simpler solution, which is simply mounting specific Linux files inside the container. Those files, for example, can be used to program the FPGA, can be used to access memory mapped elements inside the FPGA itself, essentially giving us control over this connection between the CPU and the FPGA. So theoretically, now we have Docker containers that can utilize FPGA resources. So how do we deploy them in data centers? So let's assume we have this data center here, which has a bunch of nodes. Some of the nodes have FPGAs, some have more than one, some don't have any. Kubernetes doesn't know about those FPGAs. It also does not handle them. But we create something called Kubernetes device plugin. So this device plugin gets deployed on all the nodes. It basically tries to detect whether or not there is an FPGA connected to this node. And if there are any, it becomes the controller or the manager or the provider of those FPGAs. The device plugin also allows Kubernetes to know where to deploy these FPGA applications once we try to deploy them. So for example, those yellow applications will never get deployed on a node that doesn't have an FPGA attached to it. Our device plugins are capable of supplying the FPGA as a whole. So an application can occupy the entire FPGA, or it can also use partitions of the FPGA, or what we call FPGA tenants, of course, with the addition of a hardware shell to manage that. So now we have a way to deploy FPGA-based applications in a data center. It is only missing one thing, which is the network interfaces of those FPGAs are not handled. So generally, Kubernetes handles network interfaces of normal nodes through something called a network plugin. It assigns their IPs and it completely handles them. But in the case of an FPGA, this is not possible. So we create our own network plugin. This network plugin will communicate with all the FPGA Docker containers, and it will basically it will communicate with the FPGA shell inside them, and it will assign the IPs and handle the network interfaces. Now with this entire framework, we have used it to build something called virtual network functions. Those are, for example, something like a load balancer, a firewall, or a network traffic analyzer. We built 100 gigabit per second versions of those using our FPGA, and we packed them in FPGA containers. And we were capable of deploying those in a data center using our device plugin and our network manager. That concludes my talk, and I'm going to transfer back to Naif, where he'll talk about machine learning applications. Thank you.
Cool. Thanks, Mohammed. Hope everyone can still hear me. Yeah, we're on the last leg. I promise we're almost done. Thank you everyone for sticking through with us. All right, so we talk about Aegean, which is a machine learning environment that we have on top of Galapagos. So maybe to take a step back, is a popular question that we ask is that, or a leading question here is there a framework to generate machine learning algorithms in a heterogeneous space? So when I say heterogeneous, I mean both devices and in terms of connectivity, right? And spoiler alert, there is. But if such a framework exists, can we get both flexibility and performance? So there are also off-the-shelf frameworks such as TensorFlow and stuff that can target GPUs, for example, but can we get full flexibility? As in, can I target multiple kinds of devices and multiple connectivities of devices? So we really like stacks in this group. So here's another stack. It's the machine learning stack that we've defined here. And we have 3 layers. So at the very top, we have our applications and algorithms. So at this layer, it's agnostic to the devices that you're targeting. And this is more of the application level. So in this particular level, you might describe the particular layers of your neural net, the compression algorithms that you're using. But again, totally agnostic to the devices that you're running this on. So this is where maybe your data scientists might work in. So then once you have this, you said we want to divide this up into multiple nodes and connect them together. So this is, how are these nodes connected? Are they connected via PCIe, via Ethernet? What communication protocols are they using to talk to one another? And then it's, given that we have multiple nodes talking to one another, what is the node itself? So can we change the hardware circuitry that's actually running on the individual nodes? So full flexibility allows different users to pick and choose what they want at each of these layers here. We also want this to be open such that researchers can collapse and expand this for their specific application and infrastructure. You might want to take this and realize, I know nothing about networking. I'm going to trust what these people have done for the networking stack, and I just want to change the hardware and I want to change the upper level algorithms that are supported. And if that's the case, then you could do that. Or you can work on a different layer of the stack that you're an expert in. So now that we have the philosophy out of the way, more for Aegean itself, it's pronounced much like the archipelago and the sea, and it combines 2 existing frameworks. So HLS4ML, which is a project out of Fermilab, CERN, and currently a lot of the developers are all over the world, mostly physicists on this particular platform. This takes HLS, or takes a machine learning environment and converts it into HLS IP cores. So you can, for example, in TensorFlow, describe a machine learning network and get Vivado HLS IP cores for the given layers. And given that we get these IP cores, then we plug that into Galapagos for it to deploy and connect all of these together. So should be simple, but not necessarily. This is the full-on flow here, and I'm going to get into what each of these stages are. So from a high level, all of these stages are automatic, but they are separate, and I'm going to get into what each of these stages do. So at the very beginning, for your given application, you develop your machine learning model. So fully agnostic to the hardware itself, you work on the neural net that makes sense for your given application, get an accuracy result that makes sense, and then you pump that model into HLS4ML. HLS4ML, given this neural net description, will generate the IP cores, Vivado HLS IP cores that make the most sense. And at this level, you can constantly iterate to make sure that your HLS implementation is the best possible, right? Once you have that information, then you can feed this into our own partitioner. So our partitioner is aware of the total FPGAs that we have. So you can muck around with this database that we have in the backend that says I have 10 FPGAs of this type, and we have the resource information for this FPGA. You can add other FPGAs to this database, so on and so forth. Given this information and given the IP library that I have from HLS4ML, I would partition this onto multiple nodes that we see on the right-hand side in our partitioned cluster. Next, because of the functional portability of Galapagos, we can say, I'm not totally confident to put this on an FPGA cluster just yet. could you put this on a CPU cluster first? So we can put this on a CPU cluster and seamlessly migrate bits and pieces of this CPU cluster to FPGAs without changing any user code. And if you're gutsy enough and you want to jump straight into this step, you're totally allowed to, or you can iteratively go through this. So this is a particular new flow that we can do because of the functional portability that we have in Galapagos. And this is us using this specifically for this machine learning environment, but you can use it for any distributed application you see. So for some results, we run this in our data center here, which is on the right-hand side, and it's on a cluster of these FIDUS Sidewinder boards, which has a ZG19 FPGA in them. Main important feature here is the size. It's one SLR chip, and the size is approximately of one of the SLRs in an Alveo U200, and it has a 100 gigabit UDP core, or which was developed by Clark in-house here. So the micro benchmarks, so this is the theoretical maximum I can get. This is not of our machine learning core just yet, but if things were perfect, this is what we would see. The takeaway here is that the hardware to hardware latency is really tiny, and Clark's UDP core is running at 100 gigabits per second. So if in a perfect world, we would see this kind of performance. Our first test is a small neural net, so a small amount of computation here. And when we first run this on SDXL, and we see 0.21 milliseconds of batch 1, and in Aegean, we see 0.08. So in batch 1, the latency is a 3x improvement in Aegean over SDXL, but we still see that for larger batch sizes, we see a bit of an issue, right? Because the bottleneck is the data transfer from CPU to FPGA, and which is also something that we've seen in our micro benchmarks. So ideally, we'd want to put more of the application on the FPGAs and even have FPGAs communicate amongst each other, because FPGA to FPGA communication is pretty efficient. So this is our next set of results. So we took a large autoencoder in Aegean and we split it across 3 FPGAs, and SDXL doesn't have multi-FPGA, so we just have it on one FPGA in SDXL, and we saw a 3x improvement. And this is because Aegean gives us a multi-device fabric that the user can implement larger, more performance circuits on, whereas in SDXL, you have to make use of the single FPGA that you have. So this opens the door for even more complicated circuits, like ResNet 50, for example. So these larger fabrics allows us to target something like ResNet 50, which is what we're currently working on. Our current non-performant functionality first benchmark, we're estimating about 200 images per second, but ideally we'd like to get this up to 8,000 images per second, which is like 4 or maybe like 3x better than Brainwave, but that's ideally what we're working towards. And yeah, so given that we've gone over Aegean, I would like to conclude with a roadmap of where to go from here. So let's take a step back into the high level Galapagos picture again, and let's see where to go. So for Galapagos, we need applications, and not just my multi-FPGA stuff that I'm currently working on, but maybe if you have an application that requires low-level debugging, you can bug Marco here. If you want to be able to run multiple applications on a single FPGA and need multi-tenancy, you can bug Daniel here. But we all need applications. We're infrastructure people here, and finding the right application has been the bane of our existence. Secondly, we want to be able to connect multiple like FPGA partial regions, so a lot of what Daniel is doing with a high-performant NOC. So we're looking at NachiKit for this, so hopefully we can collaborate there. And we want to deploy this to the CMC system. So CMC has their own database or data center of FPGAs, and they are willing to work with us to deploy a lot of the infrastructure that we've presented in this talk here. So ideally, if we get enough people wanting to use it, we can have them handle the admin stuff. And they are also open to using multi-FPGA, so having multiple FPGAs connected over the network switch here. So that is where we want to go long term. And on that note, I want to thank all of you for listening to us, and you can bug any of us for questions. And I will, and Nachiketa, I'll give you host privileges again.
Perfect. Thank you. That was excellent. Across so many students having sort of this smooth talk. Yeah, fantastic. Well done. Okay, so we have time for questions. And if you have a question, just shout out.
Hi, this is Zhenmei. So a great talk, is a great effort by, many students in the group. So, at the end, Lev, you are asking for applications, right? Call for applications. So we do have some, applications, like we work on machine learning, the database applications, genomics applications. So I was wondering if it's possible, for my group, I mean, this is probably a question for Paul. Is it possible for my group to get some access to the, the system that you have?
I guess with limited and with control, so we can't handle too many people, but sure, we can discuss that. And as Nate said, we're hoping maybe by the end of the summer we can get something up at CMC and more people can get access that way. Also, if you have your own hardware, this is all open source, and we're trying to, we will hope again by the end of summer have some containers that you can just deploy those, and then depending on what FPGAs you're using, if it's like an Alveo card, which we're hoping most people will have eventually, then we hope to have containers that you can just fire up your Alveo card with the container.
Okay, that sounds good. We do, have the plan to build a Alveo cluster here at SFU. So is all the software already open sourced, or is while waiting for until the end of the summer?
It's there now. It's in various states of repair or disrepair. You have to talk to Nate. But yeah, there's stuff there now.
Okay, sounds great. Okay, thanks.
Yeah, so like most of the software is there, but we currently don't have the Alveo support up and running just yet. So the Alveo support hopefully closer to the end of summer, but if you want to have a look at the current stuff, that's totally up and running. And since we have things kind of divided up into the stack here, if you have your own board, ideally it should just be replacing the shell with the shell of your own board, and all the upper layers of abstraction should work. So,
so if you want to build your own Alveo shell and contribute it back, we can do that too.
Okay. So does this, does the shell, build with your flow compatible with the Vitis flow?
No, it's not.
Oh, it's not. Okay. That may bring some challenges for us, because our application, many developers in Vivado HRS are using the Vitis flow.
Yeah, I mean it's we don't. Vitis does not plug directly into what we have. If you build like we do with HLS4ML, once you've built the kernels, then you can move those into our flow pretty easily.
Okay, that sounds good. Okay. Yeah, we'll give it a try sometime after we have this, the cluster set up. So hopefully we can build this cluster, by the end of this year. It's really very slow. I still remember when I talked with Paul, it's quite a while ago, but it took a long while, for this funding to finally arrive at my research account. Thanks, great talk.
Anyone else has questions? I have a lot, but I'm going to hold off and wait for others to ask.
Or
there
you
is a
can
prize
start,
for
let
asking
people
questions.
think.
We should have a prize for the best question or something to incentivize Q&A. If not, I'll let you think about it a bit more while I go ahead and ask a few things, right? So, so just to directly address the last comment Naif made about the NOC. So next week, my student will talk about one NOC that we've been building on the Alveo board for interfacing with the HBM, and maybe that sort of can be repurposed for use with the Galapagos multi-FPGA PR region problems that you have. We probably do need to do some floor planning, which we currently don't do, and that might help sort of localize the physical regions, right? So that you don't have the NOC floating around. It's in predictable spots inside the device. So going back to Kubernetes, right? This is something that that's very interesting to me, and I have a very targeted question about this, maybe for Evais.
Okay.
So for EC 327, which is an undergrad course I'm teaching right now remotely, we have a cluster of, we sort of have FPGA boards, pink FPGA boards connected to lab computers. And I've been debating how to make this cluster of FPGA boards available to students to use remotely. And I'm wondering whether Kubernetes can provide user level control so that only one user gets to use one FPGA at one time. And maybe there is some timeout, right, that you use for half an hour and then you get kicked out so that somebody else can come in. Can your framework or does Kubernetes provide some of this support already, or would that be orthogonal to what you have in mind?
Okay, so 2 points here. The timeout thing is already a function of Kubernetes. So if we manage to have the FPGA inside Kubernetes, then this part is already done. It's already there. Having an entire FPGA per cluster is, so let me start from something here. So first of all, we have device plugins. It's not something we made, it's something that's already there. We just made our own for FPGAs. For example, NVIDIA makes device plugins for their GPUs. Xilinx actually has a device plugin for their FPGAs. Naturally, the device plugin will deal with the entire resource as a whole. It will not partition it. So for example, if it's a GPU, you will get the entire GPU. You cannot say, hey, I need 2 cores out of 4. It's just, you get the entire 4 or you get nothing. So by default, this is what you get with the device plugin for the FPGA. You can do that. Our device plugin has the flexibility that you can partition the FPGA, but this is not your question, right?
That's right. Yeah, I can allocate the entire FPGA.
Yes.
We are using Pink, so would that work with the, so how do you package your FPGA application? Do you have the bitstream and the host code sort of as one unit that is presented to Kubernetes as here's the application you run? How do you package up the application?
Okay, so the thing I presented was mostly targeted for virtual network functions. So we do the following. We have bit streams. The bit streams are essentially a shell for the VNF, which has some network interfaces and so on, plus a user-made hardware. And then we have an accompanying software piece, which is usually a RESTful API or some configuration programs and so on. We package them together in one Docker container. So the Docker container, you will just copy the software, you will copy the bitstream, you will run one command, which will download, it will not be a run, it will be a CMD or an entry point, for example, which will download the bitstream onto the FPGA and then start running your accompanying software.
Mohammed, if you want access to the slides to go through it, you can request it if that helps.
I have not the slides I presented today. I have something. Let me find it out first, and then I'm gonna share. I think.
Yeah, so for 327, sort of the package that I get from the students is their bitstream at the end of the day, and some Python scripts that program the FPGA from the ARM processor inside the FPGA itself, right? So there is a host Windows machine, x86 machine that is connected to the FPGA board, but sort of everything happens from the ARM control point, right? So when you create this sort of Kubernetes cluster, your Docker container is on the Windows or whatever, the x86 host, right? And then you have these file mounts or whatever that let you program bitstreams, the same data back and forth from into the FPGA. would that work with the ARM sitting on the
We
SoC?
actually have it on ARM. We didn't test it
Okay.
on x86 yet, but it
Okay.
works with both.
Okay.
You can have the same container. So fortunately, Docker Hub supports multi architecture containers. So you can actually make containers for both, and Kubernetes will pick the right one, the correct one for depending on the node you're running on. Naif, would you disable your screen sharing so I can share mine? Okay. Host disabled participant screen sharing. Sorry, I'm not sure if it's your Naif.
Oh, and Nachika will have to enable
Oh,
that.
sorry. Okay.
Yeah.
Okay.
Okay. So I've made you host.
Okay. Let me share the screen. Let me make this a bit, get out of my way. Okay. Something is wrong. One more. Okay, so this is essentially what we have in our work. So for example, we have those green things, the config and the RESTful API. Those are software components that we run on our ARM core. And then we have this FPGA shell and a user-defined hardware that are on the FPGA. And what we do is, can anyone? Yeah, okay. What we do is, for example, we pick an Ubuntu image, we copy the configurations inside it. We also copy the binary file, the bitstream file. And you can, in the command here, for example, this is how we download the bitstream, and then we run our interface API, and then we have a full co-software hardware image thing running in our container.
So the firmware here has the Xilinx drivers for downloading the bitstream to the FPGA.
Yes, we have to mount this path inside the FPGA, inside the Docker container. So these paths are not mounted by default. So actually, in my presentation today, when I said we mount some paths for this, we have exactly two paths. One is this, which is for the firmware downloading, and the other is /dev/mem, which is just to access memory mapped AXI components inside the FPGA.
Right. One quick clarification. So this ARM64 V8 to Ubuntu 18.0, that's just a stock image. You didn't get any specialized Xilinx build for? Okay.
No.
Okay. So the sort of
in fact, this might be big. I could go for an Alpine image and it would still work fine. It's just I picked Ubuntu. I was testing.
So how do you do memory mapping or sharing a memory region between the ARM and the FPGA?
So some of, as long as we use AXI interfaces, so some of the,
I see.
Yeah, we just have memory mapped interfaces. So one of those, like those two programs, these are C++ programs. They access dev mem and they use it to just allocate memory in specific locations, which is the memory mapped components.
Thanks. That's very, very useful. Okay. I'll maybe follow up with you offline as well.
Sure. Yeah. Okay.
I had one question for Clark, I think. I think you were talking about the data center interconnect, right?
Yeah.
Okay. So when you were discussing putting switches in the FPGA, was that to complement, I didn't quite follow, was that to complement the ASIC switch? Or were you completely removing the ASIC switch from the picture and just sort of moving data between FPGAs to get it to the right FPGA you wanted to get it to?
Sorry, could you repeat? Sorry.
So do you still have an AXIS ASIC switch in your system, or the switching is done entirely between the FPGAs themselves?
Yeah, the switch is made by FPGA.
Completely inside the FPGA.
Yeah.
Did you have a head-to-head comparison between your FPGA solution and the ASIC solution? What would be sort of the performance advantages of doing this switching entirely in the FPGA?
So if you go through, usually the conventional network switch is an Ethernet switch.
Right.
So if you go through the Ethernet switch, the biggest advantage of our system is the latency. So if you go through a network switch, Ethernet switch, it's usually bigger. The latency is usually bigger than 1.5 microsecond per hop. But like for our infrastructure, we can make it under 300 nanosecond per hop.
I see.
Yeah. And also we provide reliability, which is not provided by the conventional network stack.
And one sort of allied question was the sort of power or energy overhead. Because you're doing multi-hop, you're going to be accessing multiple sequences of FPGA IO pins, right? So instead of going to one central super optimized ASIC switching fabric, sure, it's slow, but do you imagine there might be power or energy overhead to going through lots of FPGAs as an alternative? Or do you have power measurement infrastructure that
We currently don't have this result. Yeah.
Okay.
Yeah, but I don't think we'd have many more switches than a standard infrastructure, because with big enough FPGAs, you can build, 32, 64 port switches in an FPGA, and
right.
that's not much different than what's already out there.
Right. I was thinking more of the multi-hop solution. So if you had a distributed switch across the entire fabric, then you would be traversing through several FPGA hops to get to the destination. And I was wondering, if that was comparable in terms of power or energy efficiency.
Yeah, but I think in depending on the topology of your data center, it's the same number of switches. So.
Right. Okay. Does anyone else have a question? Because I just have a couple more. Can yield to let somebody else ask a question. No? Okay. So I have a question for Rafi with two eyes.
Arjang.
So
yes, sir.
You mentioned something about an Axis Snoop circuit that you were looking at for trying to measure properties of your design, right? So is this a standard IP, or is this something you developed to try and record these statistics?
It's a IP that I developed. It simply monitors axis streamlines and collects certain information on the traffic. So being that the number of flits that pass through, the number of packets, the duration of measurement, which combined with the number of flits and packets can give us some meaning of throughput, and then the average packet size as well.
Right. And so this is a sort of a standalone Snoop circuit that sits at different spots along the network, right? If you want to measure latency, how would you do that? Or that's not something that a single instance can do. So you need to sort of coordinate across multiple snooping circuits to get end-to-end latency?
Well, these are two different cores. So the packet snooper is completely separate from the latency stuff. The latency measurement, as I mentioned, is done by using the PTP protocol, where you put two different cores in two different places. It could be the same FPGA or two different nodes within the cluster, two different FPGAs. And then by sending packets, timestamp packets from one node to another, typically one-way trip, Oh,
I see. Okay, understood. But then you would still need to, you won't be able to trace the latency of every single packet, because that would just be a lot of timestamps that you'll have to record, right? Or
well, you do have the option, but but I mean, there should be some balance, to avoid congestion.
Right. Yes, I had one question for Camilio about the storage wrapper for RDMA. Maybe it just went too fast for me to fully understand what was going on, but can you clarify? Can you clarify whether the RDMA wrapper that sits on top of your storage device, that's also implemented on the FPGA? That's the ship FPGA that you talk about? Okay.
Yes, it's implemented on an MPSoC device. In particular, many of the Linux operating functions are offloaded to the ARM side of the MPSoC environment, but the data path is all FPGA.
Oh,
I
wow.
parse the RDMA with FPGA, figure out where it should go by talking with the ARM, and then send the data off directly from the FPGA.
So you're using the hardware acceleration to try and move data as quickly as possible without going through the ARM
yes,
OS.
the ARM is just for the control path of.
Right. So you mentioned this figure 294 megabits per second, right? And that was for a remote access from another FPGA to your storage device.
294 megabytes
per second. Okay, sorry. What would be the figure if the ARM that connected to the storage device was to access that particular device without any remote access whatsoever?
I hadn't considered that test case, particularly because the ARM is so busy keeping up with all of the demands from the FPGA. I don't consider it as a usable node for any other purpose other than assisting the ship system in doing the Linux processing parts of the design.
I mean, it's mostly an academic question. I just want to know how fast could you have run it if it was a purely local access? And what does the datasheet say about that memory device, right? That how fast could you theoretically access it? And does 294 megabytes per second, is it 99% of the theoretical speed possible for that device, or how far away are you from that?
I am still a little bit far away. I'm operating at about a quarter to a fifth of the theoretical maximum. But I'm right now working on many performance limiting bottlenecks that once eliminated, I should be able to greatly increase the performance of the system.
Understood. Okay. That was my question actually. Yeah. If it was local, you theoretically might be able to get that. Maybe the ARM can't really saturate that bandwidth either, but yeah.
I'm using 100 gigabit per second network, so the factory remote really plays little role in the throughput part. A little bit with the latency, but not with the throughput.
Right. Actually, I had one last question for Daniel. I think one of the earlier speakers about in his sort of high level block diagram, he showed a bandwidth shaping interconnect. I was curious what you meant by that.
Right. So the bandwidth shaping interconnect, I guess it was to save space in the diagram. It's actually a standard interconnect with bandwidth shaping like throttlers at the outlet of each of the application regions, where I use a credit-based system to throttle the bandwidth to some user set.
So you can sort of program the maximum burst size or the maximum injection rate from those endpoints. Okay, perfect. Understood. And one allied question to that is what was the cost of the shell in percent dots or percent registers?
I don't have that on the top of my head. I remember it. So there are some components that were parameterizable. So specifically on the network side, the NMU that changed a lot. So I think the actual the other components outside of that were somewhere between 5 and 10%, I think, of an alpha data 8K5. No, it was not the MP sock, an alpha data 8K5, if I recall. It might have actually been even less than that. I don't remember specifics, but it's been a while since I actually profiled the numbers.
Right. Cool. Thanks. Maybe one more question for Naif at the very end. So at the end, you talked about combining, sort of having an application machine learning stack that uses all these features. Did you use every single feature that was discussed today?
That's on the to-do list. Not yet. So there are, I actually, yes and no. So there's a few features, like some of Daniel's stuff I haven't been able to put in just yet, and I think that's on like the to-do list to do very shortly. But because this machine learning application has been quite, at least to get the first iteration through, is can be quite difficult. I've had to actually use a lot of Marco's and even Arjang's debugging and profiling stuff that I that otherwise hasn't been totally formally integrated into the stack yet, but I've needed it, and I can say like user testimony for it that their stuff's pretty good. So in some ways, yeah, I've used quite a bit. So I've used a lot of Clark stuff, Marco stuff, and Arjang stuff. So, but the rest of the stack, not yet.
Sorry, I think I may have missed a few students. I didn't ask questions to every single one. I apologize. But I mean, we still have some time for any of our other 33 or 23 participants minus Paul's students to ask questions to the students I forgot to.
And I guess like once the presentation's up, like I think most of us are on the Slack channel, so you can like message us, any of us, and we'll be happy to talk or email or whatever. So
yeah, it's a good reminder. I actually didn't create a channel for you guys. I probably should create a channel.
Oh yeah, yeah. That'd be even better if we're all in the one channel.
Yeah, it's a hashtag Galapagos. So, oh, so maybe a question for Paul. What does Galapagos really mean here?
We were looking for a name.
I want to know too, by the way.
It's so I guess it's a collection of islands, and with so it's an example of a famous archipelago.
Right. Okay.
So.
Got it.
Yeah, it's not an acronym. We just decided a theme.
Right. Cool.
I initially wanted to name it what was it, Trebuchet, as to one up Catapult, but that got turned down.
That was too confrontational with Microsoft.
Yeah.
And they're bigger.
I did like the fact that you're trying to beat Brainwave by what, 3 or 4x. Yeah, very ambitious, but good. Yeah, good sort of target to have.
Okay, so a few of us have to jump onto another call in 2 minutes.
Last opportunity to ask questions, people. Yeah, we really need to incentivize questions here, don't we?
Well, yeah, Slack's a thing, so that's totally fine.
You can think about it and then maybe message people on Slack. And yeah, Galapagos is partially open source in some states, so it's something that people can try out and see how to make it work for their applications. All right, so with that, if nobody has any questions, then thank you all for second week. We've had a very good start. Next week, my student will be talking about the NOC that you thankfully mentioned at the very end. And hopefully it will serve some purpose for the Galapagos framework as well. All right, then. Thank you, everyone.
Thanks, Nachika, for organizing.
And happy belated Canada Day.
Yeah. And I think Mohammed looks like he's in control at the moment. So.
Oh, yeah, I got to reclaim.
I am?
Oh, yeah, just.
Oh,
go to reclaim.
I didn't know.
I guess give Nachika host privileges just in case he needs it for the video.
Yeah, I got it back.
I
can take it back anytime I want. Yeah. All right. See you guys next
Okay,
week.
bye.
Thank you. Bye.
Bye.
Thank you.
Bye.
Bye.
See ya.